Hello, this is Group 20, the Advanced Breadboard. This is our project. My name is Christian Gutierrez. I'm the CPE. This is Amar Mubarak, she's an electrical engineer, and this is Sharon Sloan. She's a computer engineer as well.
So here you can see what a regular breadboard looks like, and here's what we made. This breadboard has some advanced features that a regular breadboard doesn't have. It connects to software where you can build your circuit and learn how to place it on a breadboard, while also checking to see if you have an open or short circuit. This breadboard is designed in a way to have priority on portability and accessibility.
So when designing the PCB, we had to pick out several layouts and components in order to get our breadboard design working as intended. A couple key components that we use is an INA 219, which is a voltage, current, and power sensor. Since we're utilizing the voltage and current sensor for our design, we incorporated this component in order to detect open and short circuits for our advanced breadboard. The second component that we use is a TPS 61023. This is a boost pass-through voltage regulator. What this means is that when the input voltage is lower than the voltage output, which is 3.3 that we require, it's going to boost the input voltage to 3.3. And if it goes higher than 3.3, it'll just pass it through. So for an example, if the batteries were to output 3.4 volts, the voltage output from the regulator would be 3.4 volts. The reason why we decided to go with the boost pass-through is because we're using batteries, and as the batteries drain, we're using two AAA batteries, and as they drain, their voltage drops. So requiring the use of a boost pass-through was very critical for our hardware design. The third thing that we used is the ESP32. This is the brain of our advanced breadboard. This would help us translate the algorithm from the Raspberry Pi into the LEDs as well as the sensor in order to get the information that we require so that the LEDs can correspond to the correct node, and as well as being able to communicate with the sensor for an open and short circuit detection. And that is the hardware approach that we decided to go through. We also incorporated some batteries in order to pre-program the software on the ESP32 as we wish. That way we can do easy edits and as well as creating updates to the software if required.
For the software approach, the main important thing about this project was the GUI, which is just a user interface that users or other students or whoever may use this project can interact with. And so on this user interface, in the software approach, we decided to make a sort of simulator similar to other programs such as Multisim, where people are able to create their own circuits, and as well as using those other tools such as labeling them and editing their values and so on and so on. Additionally, the main portion of this is to be able to have a translate feature, which also is incorporated within the software approach. And so what that means is that on the GUI end, there's also background files which allow a translation to occur, and as such, show that translation of the circuit that the user made onto the screen. Along with that, there is other things that the user does not see, such as the logic behind placement of components and deleting these components, and other short and quality of life features.
With the ESP32 on the PCB, we're able to integrate hardware and software. So the chip will use serial communication with the Raspberry Pi. This cable will be used to allow the Pi to send a matrix for which LED will turn on based on the schematic the user made. The ESP32 will then return current and voltage values of the user circuit using the serial communication. This type of communication requires precise timing and correct syntax to ensure the messages maintain integrity.
So the reason why I worked on this project is through my own personal struggle working with breadboards. Being able to translate a linear circuit schematic into a breadboard design was really a struggle for me in the beginning of my engineering career. So being able to work on this project really helped me trying to help other students to kind of get past the struggle as well. And that is the reason why I decided to work on this project.
Similarly to Amar, I also had my own struggles, and so a lot of this happens during school. And so the reason I worked on this project is to avoid these sort of silly errors that somebody might be making as a person learning how to make circuits. And so my main goal and my main reason was to help myself and other students alike in the engineering field trying to learn how to use circuits.
I joined this project because I feel like this design has a really big opportunity for at-home use. You know, people who want to build circuits at home and they just struggle or make mistakes that they're not quite aware of. It's a great tool to get you included into the industry.
So a couple feedback that we got when working on the hardware design of this PCB is that Dr. Weeks was able to help me identify a few issues that we kind of had in the beginning. Mainly was button layout and button routing through the PCB. It kind of caused an issue with booting the software for the ESP32, but we were able to fix that in the second iteration from that feedback. Another thing that we did do, that we did more efficiently on the second iteration, is the location of the vias. In the second design, we were able to spread out these vias so that way the ground planes from the top and bottom layer are able to connect together easily, allowing for better grounding. We fixed that in the second iteration, and those are the feedbacks that we mainly earned for those two iterations.
So as Amar has kind of already touched on, we definitely looked a lot for feedback and tried to incorporate it as best as possible. For the software side, it was extremely important, especially for the GUI. Considering that this project was meant to be like a tool to help other people, it is important to get the feedback of other people to then tell us what they feel can help, boost the productivity of how they use this project, or just help them learn circuits in general. And so on the software side, we had a lot of feedback in terms of actual, user interface, in terms of accessibility, and general features like that.
For the integration part, some of the feedback I received from Dr. Weeks was needed for the Raspberry Pi, which was getting a low voltage error. So we were able to fix that by creating a new wire that was able to handle the amount of voltage and current that we needed to go to the device. So without that error, that feedback was really appreciated. So thank you for considering our project for the showcase. We hope to hear back from you.
So here we have a short demonstration. As you can see, we're making a circuit where we have a ground, resistor, and power source all in series. And so when we translate that circuit, we have 3 nodes in use, and so that will be demonstrated and translated properly onto our actual advanced breadboard. And so here you can see those 3 corresponding dots here are going to turn on here, which represent the nodes that you would need to use. So at this point, this is where the user would then make the circuit. So now that the user has made the circuit, they can then check to see if they're getting the correct values that they would need. So for example, if we are anticipating 6 volts and 21 milliamps, then we would be fine, which we are according to the power source that we are using. And so we see that the sensor data is being able to be displayed as the user makes their circuit. And when they decide to incorrectly make their circuit, for example, here they took off the ground wire, and so now there is no current, and we're given the warning that there's a potential open circuit.